Let's work on some more balancing of chemical reactions or chemical equations. So here I have a cobalt oxide compound reacting with carbon, forming cobalt metal and CO2 gas or carbon monoxide. Notice here this, because you should be practicing your naming as well. Remember the oxygen has a -2 charge. There's overall three of them, so -6, meaning the two cobalts have to have a +6 charge overall. So this cobalt is a +3. So I will call this cobalt 3 oxide. Cobalt 3 oxide reacts with carbon to form cobalt metal. When it's just a solid form, you just call it what it is, it's just a metal, and then carbon dioxide. As before, I'm going to write down the elements I have. I have CO, O, and C on each side of the reaction. By the law of conservation of mass, what goes in has to come back out. So at the start, when I look at my cobalt, I have two cobalts over here, I have three oxygens here, and I have one carbon here. When I look at the other side, I have one cobalt, one carbon, and two oxygens. Now, some students may want to just start with the cobalt 'cause it's the first thing listed, but trust me when I say when you have something like this combination going, just do it first because oxygen is rarely by itself. And if it is, it's by itself in the form of a diatomic. And so it can cause other issues for other elements because it's usually paired up with something else. What I mean by that is it's going to change the number of a different element you have in your reaction. So go ahead and get those oxygens balanced first. You need the lowest multiplet here because there's no commonality between 3 and 2. So I'm going to multiply this by 2, giving me an overall 6. So a 2 in front of here. Take that out of the way. I'm going to multiply this by 3, giving me an overall 6. So my oxygens are balanced. But notice when I put the 2's in front of those pieces, in front of CO2, O3, and CO2, it changes to other elements. So now my cobalt on the reactant side is 4, and my carbon on my product side is 2. Now it doesn't matter which way you balance it, truthfully, just go ahead and balance it. I've now got 4 cobalts on my reactant side, so I'll multiply this by 4, giving me 4 cobalts over here. Again, it doesn't matter because at this point, the cobalt and carbon I have to balance on the opposite sides are singly by themselves, so it's an easy balance. Multiply this by 2, giving me 2 on each side. So I have 2 cobalt 3 oxide reacting with 2 carbon, giving me 4 cobalt and 2 CO2. And again, I'm going to include those phases in there. So the cobalt 3 oxide is a solid, carbon is a solid, the cobalt metal is a solid, and then CO2 is a gas. Let's look at our next one. Okay, this next one is an example where you can keep your polyatomic together. Notice here I have the phosphate polyatomic. So I have strontium chloride reacting with lithium phosphate. So again, strontium, I'm going to erase this in a sec, but strontium chloride, lithium phosphate, and you're producing strontium phosphate and lithium chloride. We'll learn about this soon, but this is called a double displacement reaction. Basically, everyone just swap partners. But I do see phosphate here, and I know phosphate is one of my polyatomics, and it's not breaking apart. Because it's not breaking apart, I'm going to leave it together in the balancing because it makes my life easier. You don't have to, and I'll show you what I mean by that in a sec. It will work either way, but I recommend if your polyatomic stays together, keep it together in the balancing. So I've got strontium, chloride, lithium, and then I'm going to write phosphate here. I could write phosphorus and oxygen and balance them individually, but I'm going to write phosphate overall. Strontium, chloride, lithium, and phosphate. Phosphate's the only one I'm going to write the charge on just because I'm reiterating in my own brain as I'm learning these things that phosphate is a 3- charge, okay? You will still balance it correctly if you wrote just PO4, but I don't want you to do that because I don't want you to mess it up long term and then forget that it's actually a 3- charge when it matters. So let's write down how many I have of each thing. Strontium on the reactant side, I have 1. Chlorides, I have 2. Lithium's 3, and phosphate's 1. Excuse me. On my product side, strontium, I have 3. Phosphate, I have 2. Lithium, I have 1. Chloride, I have 1. It truly doesn't matter what you're going to balance first here. Let's just go ahead and start with the first one. Let's start with strontium. So I've got 3 on one side, so I need 3 on the other. So times 3, I put a 3 in front of that. But notice that changed my chlorides. So now I've got chloride times 3, giving me 6. So let's go ahead and balance our chlorides. Well, now I need 6 chlorides over here. So I'm going to put 6 in front of the lithium chloride. But that also changed my lithium. Now I need 6 lithium on this side. So multiply that by 2, because I already had 3. Multiply it by 2, and I will rewrite this below in just a sec. But 2 of the Li3PO4 gives me 6 lithium. That changed my phosphate. And now my phosphates match. So 3 strontium chlorides. Remember, aqueous means it's dissolved in water. 2 lithium phosphates. That's also dissolved in water. It's aqueous. It's what's allowing these things to react. This will form solid strontium phosphate. I have to put that phosphate in a parenthesis because I need 2 of that phosphate ion there. And if I didn't write a parenthesis, SR3PO42 means 42 oxygen. You can't have that. When you have a polyatomic and you need more than one of them, you got to put it in a parenthesis. And then lithium chloride aqueous. So we'll talk about this in the next chapter as well, but the driving force of this reaction, the whole reason it occurs, is the solid formation here. It's kind of important to start thinking about those things, what we call driving forces. Why does a reaction even occur? And this top reaction here is actually shown by the pictures here. I have ammonium dichromate, and it's decomposing. So when you have just one reactant going to products, it's called a decomposition reaction. It's decomposing to form something. So the ammonium dichromate is forming chromium 3 oxide, nitrogen gas, and water vapor. But if I look here, it's actually balanced. And that's what's going to happen with a decomposition reaction. If you just have one reactant making the product, it can't make more than it already had. But the reason I have this example in here is that I have a polyatomic here and a polyatomic here. I have NH4 plus and I have Cr2O7, 2 minus. But notice I don't have any of those on the other side, so I can't leave it as a polyatomic when I'm balancing it, even if I'm just checking it to make sure it's written right. So I've got nitrogen, hydrogen, oops, sorry, chromium and oxygen, nitrogen, hydrogen, chromium and oxygen. On the reactant side, I have 2 nitrogen, I have 2 times 4, I have 8 hydrogen, I have 2 chromium, and I have 7 oxygen. On my product side, I have 2 chromium, I have 3 oxygen, 2 nitrogen, oops, 4 times 2, go the other way on that one, 8 hydrogen, and then I have 4 more oxygen, giving me my 7 oxygen. So it's still balanced. I just want to always check to make sure it's balanced or we got some other problems going on. Okay, what about combustion? Combustion is when you burn something. So you guys are specifically responsible for combustion of hydrocarbons. For predicting the product, you should be able to write the entire reaction of the combustion of a hydrocarbon or a carbon compound containing carbons, hydrogens, oxygens. Anything else combustion-wise, I would tell you what else is produced, okay? But combustion, so if you're gonna burn a hydrocarbon, hydrocarbon just means carbon, hydrogen containing compound, hence the hydro and the carbon. Or a compound containing carbons, hydrogen, and oxygens. That's what you're responsible for. When this undergoes complete combustion, you guys are responsible for complete combustion in oxygen. What that means is it reacts with O2. So I can say something undergoes complete combustion. You need to know that complete combustion means it reacts with oxygen gas and it forms CO2 and water. So it reacts with O2, and the products are CO2 and water. Complete combustion, and that's what you're responsible for. The products are CO2 and water every time. Now notice here, it does say water liquid. In the picture, it does say water gas. Technically speaking, at the temperatures you're at, it is a gas, but you will see it written as a liquid in some textbooks in some examples, and that's why I have it written as a liquid. I'm not picky on that specifically, as long as you pick liquid or gas. Do not tell me water is a solid when you've combusted something. So again, you need to know that a compound reacts with O2 to form CO2 and water. Incomplete combustion, you are not responsible for predicting, but you should understand what incomplete combustion is, because as a human in this world, it's important. Incomplete combustion is when the products are CO and water, so carbon monoxide and water instead of carbon dioxide and water. So this is due to an insufficient supply of oxygen during the reaction itself. Basically, there's not enough oxygen present to actually form the CO2, so CO forms instead. But it's incredibly dangerous for us as humans. We survive by breathing oxygen. We need oxygen throughout our entire body. So we breathe in the air around us. Our body filters that out. We exhale the CO2 and anything else that may be in the air. And then our body grabs that oxygen and transports it through our entire body. The problem is that CO bonds better to the hemoglobin in your blood, which is transferring the oxygen throughout your body. CO binds better than oxygen does. A hemoglobin can bind 4 oxygen molecules at a time. And the first one to bind is kind of difficult and actually changes the conformation slightly or the geometry slightly of the hemoglobin molecule. And then so the second one's slightly easier to bond, third is easier to bond, the fourth is easier to bond. But it's because of the size of the O2 molecule. The CO molecule is smaller, so it's easier to bond it. Not a good thing for us. And that's why I feel it's important that you understand what incomplete combustion is, but you absolutely must know how to do complete combustion. Okay? I won't ask you to give me the products of incomplete combustion, but you should understand it. Okay. So let's do an example. Aluminum metal reacts with air to produce a white powdery compound, aluminum oxide. What's going on here? If this is what I gave you as the example, you should be able to give me the entire balanced reaction. So first up, you ask yourself, well, what is reacting? I've got aluminum metal reacting with air. Air isn't very specific. Why do we say air? I don't know, it's probably because it's easier. But air, when we say it's reacting with air, we really mean it's reacting with O2. It's reacting with oxygen gas. What's being produced? It's producing a white powdery compound. It's producing aluminum oxide. What are the formulas of each reactant and product? Well, aluminum metal is just aluminum. I know oxygen is one of my diatomics, so remember your diatomic and polyatomic elements. Okay, that is very important. Oxygen is O2. And then aluminum oxide, I know oxygen is O2 minus. I know aluminum is Al3 plus always. Therefore, the formula must be Al2O3. And I know it's a solid because it says it's a white powdery compound. I'm not going to describe a liquid or a gas as powdery. Write the correct formulas for each species. So I've got the aluminum plus the O2 on the reactant side, the Al2O3 on the product side. Write the correct phases for each species. Aluminum metal, metals are solids. Only metal that is not a solid is mercury. At 25 degrees C. So if you're at 25 degrees C, standard conditions is where we're expecting, unless we otherwise state it under standard conditions, all metals will be a solid except for mercury. Mercury is a liquid. Oxygen is a gas. We know that because we're breathing it. And Al2O3, again, is a solid because it is telling me the word powdery. Powdery suggesting solid. And then balance it. When I look at this reaction, I see that 2-3 combination. I'm going to get rid of that first. I'm going to put a 2 in front of the Al2O3 and a 3 in front of the O2. So a 2 and a 3 here. That balanced out my oxygen. Now I need to balance out my aluminum. I now have 4 aluminum, so I'm going to put a 4 in front. Okay. Write the complete balanced equation for the complete combustion of ethane, C2H6, and oxygen. Now, most of the time, what I will just say is write, I will just say write the balanced equation for the complete combustion of ethane. I'll just say it like that. I won't even tell you the other words. Okay. Here, because we're still learning it, I'm trying to remind you guys it's an oxygen. Normally, I won't say that. I'll just say, what is the balanced equation for the complete combustion of ethane? That's all I'll say. So write down what you got. You got C2H6 and I didn't tell you, but I will tell you, ethane is a gas. It reacts with O2, which is a gas, and it's going to form CO2 and water. So I have to know it's reacting with oxygen. I have to know its products are CO2 and water. Write down what you got. You got carbons, hydrogens, and oxygens. Carbons, hydrogens, and oxygens. 2 carbon, 6 hydrogen, 2 oxygen. 1 carbon, 2 hydrogens, and 2 plus 1, 3 oxygens. When you're doing combustion, balance oxygens last. In the previous example, I had you balance it first. Trust me, just balance it last. It's split across a couple different compounds. Get the rest straight, then we'll deal with your oxygens. For combustion only, do them last. Let's go ahead and do your hydrogens first. Times 3 gives me a 6 here, but that changes it here. So 2 plus 3 now, giving me 5 here. Now I'm going to balance my carbons. Times 2 gives me a 2 here, but that also changes it here, giving me 4 oxygens here, and now I have 7 oxygens overall. You can play with this back and forth, but it's going to be a pain to get it to balance. What I recommend when you have this combination where you have an odd number over here and the diatomic here, you are temporarily going to do a fraction, okay? You're going to take the numerator here and the 2 down here is your denominator, and you're going to write 7 halves. So the numerator becomes the numerator of my coefficient, and the denominator becomes the subscript on the oxygen or the diatomic on your reaction side becomes a denominator. 7 halves of O2, that's 3 halves times 2, that equals 7. The reaction is technically balanced right now, but you are not allowed to leave it in fractional form. So now what I'm going to do, so again, if needed, check for fraction. If you need the fraction, the numerator is the number from the product side. The denominator, if you're dealing with the diatomic, will be 2. But then you must multiply through the reaction. Sorry, I gotta move that. By that denominator. To clear that fraction. So I'm gonna get rid of the stuff down here. We'll recheck that in just a sec, okay? Just for space. I'm going to go ahead and put a 2 in front of here because I'm multiplying through by that denominator. That gives me a 7 here because 7 halves times 2 is 7. I got a 4 here because 2 times 2 is 4. And I had a 3 there that I just erased, so 6 here. Now it should be balanced, but go ahead and check it anyway. Carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. Now I have 4 carbon. Now I have 12 hydrogen, and I have 14 oxygen. The other side, I have 4 carbon, I have 8 oxygen, 12 hydrogen, and 6 more oxygen, 14 oxygen. So now it has been balanced. Fractions make the balancing easier when you have a diatomic and it won't easily balance. That doesn't mean you always use a fraction with diatomics. You have to pay attention to the compound itself. So let's look at the next one. When the balanced equation for the complete combustion of ethanol, CH3CH2OH, is written using the smallest whole number coefficients, what is the coefficient on oxygen? I recommend when you're given something like this to put the formula together, meaning put all the carbons together, all the hydrogens together, all the oxygens together, because it's easier to see. It's less likely to forget one. So I've got C2H6O. It's the same thing, doesn't matter, it's the same formula. And all we're trying to do right now is balance formulas, okay? You don't have to do it, but I find it better to be better for students that way. Ethanol is a liquid, and I would tell you that if you needed that information. Reacts with O2 gas to produce CO2 and water. Carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. 2 carbons, 6 hydrogen. Now, I like to forget the oxygen right here. Don't do that because then you don't get the right answer. And I usually figure it out before it's too late, but you may not. So don't forget that oxygen right there, okay? 1 plus 2 gives me 3. 1 carbon, 2 oxygen, 2 hydrogen, and 1 more oxygen. Oxygen probably aren't going to stay balanced. Let's go ahead and do everything but the oxygen first. I'm going to start with the hydrogens. So times 3 gives me 6 hydrogens on that side. Now I got 5 over here. Let's balance my carbons. Times 2. Yep, 2 gives me 2 carbons on each side. My carbons are balanced. That changed my oxygens. So 4 plus 3 equals 7. Now I only have 3 on the other side, but I have 1 hanging out by itself that can give me that odd number I need. So I'm going to say 1 plus 6 to give me 7 to get the 6 here. I just need a 3 right here. So sometimes you need a fraction, sometimes you don't. It really depends on the system itself. There's not an easy answer to that. You just kind of got to practice them and see what comes out. Okay, what about this example? Or these 2 examples. Write the balanced equation for the reaction of solid potassium chlorate decomposing from solid potassium chloride and oxygen gas, or to form solid potassium chloride and oxygen gas. So first, potassium chlorate. Potassium is K plus, chlorate is ClO3 minus, so I just need 1 of each. KClO3, and it tells me it's a solid. That's decomposing to form solid KCl and O2. Now, I have to balance this thing. I have that combination of 3 and 2 oxygens. Not helpful. 3 and 2. It's the only way to get rid of it. But now I have 2 potassiums and 2 chlorides. I need 2 KCl on the other side. And the last one here, given the balanced equation for solid iron 3 sulfide, give the balanced equation for solid iron 3 sulfide reacting with gaseous hydrogen chloride to form solid iron 3 chloride and hydrogen sulfide gas. Okay, iron 3 sulfide. So that means Fe3 plus and S2 minus. So Fe2, S3, and that is solid. That's reacting with hydrogen chloride gas. So HCl gas. It's forming solid iron 3 chloride, FeCl3. Sorry, I have a hard time writing on the bottom of my iPad. And I'm also not at an easy desk right now, so it's making it slightly more difficult. And hydrogen sulfide gas, H2S. Because again, hydrogen is a +1, sulfide is a 2 minus. I need 2 of them. So, doesn't really matter where you start here. See, I've got 2 iron, 2 iron. That gives me 6 chlorides, 6 chlorides. That gives me 6 hydrogen, 6 hydrogen, and that balanced out my sulfides.